This is the second half of lecture notes 10. Here we are going to follow along in the book's example of threats to internal and external validity. We're going to look at the relationship between student-teacher ratios and test scores in California and in Massachusetts. So we're going to try to find out if the population studied in California is the inferences in the population studied, or the inferences in California, are valid for Massachusetts. Can we extrapolate the findings to places like Massachusetts? All right, so the objective is to assess the threats to internal and external validity of empirical analysis of the California test score data. The external validity test, we're going to compare the results for California and Massachusetts. The internal validity tests, we're going to go through the list of the 5 potential threats to internal validity and think hard about how each of them could be affecting our results. So check of external validity. We're going to compare Massachusetts and California results. The Massachusetts data set, we have 220 elementary schools. The test is the 1998 MCAS test for math, English, and science. The variables are student-teacher ratios, test scores, percent EL, and lunch, fraction of students receiving free lunch, and average district income. So the first thing we want to do is compare California and Massachusetts data. The average test scores are higher in Massachusetts, but that's just because the tests are different. So the left-hand side variable, test scores, is measured differently. So a direct comparison is invalid. The average test score in California is 654.1. The average test score in Massachusetts is 709.8. But that doesn't mean that students are doing better in Massachusetts. It's just a reflection of the different test. So we'll need to normalize the test score somehow. Student-teacher ratios in California are higher, 19.6 on average, with 17.3 students per teacher on average in Massachusetts. So that's going to play a role. The percent of English learners in California is higher, 15.8 versus 1.1% in Massachusetts. So that's also going to play a significant role. We have a higher fraction of students learning English in California than we do in Massachusetts. And the average district income is lower in California, but the standard error is higher, which suggests that there's a larger spread of income. So there's richer people. The variance of incomes is higher in California, essentially. So all of these data points could be indications that our results will not be externally valid to Massachusetts. But let's estimate the model on Massachusetts data to find out for sure. Okay, the second thing we want to do is look at the relationship between key variables, income and test scores. In California, we saw this before, that there's a nonlinear relationship. So the line of best fit for just a simple linear model of test scores on income, that doesn't fit the data very well. It over-predicts over here at high levels of income, and it probably under-predicts somewhere in the middle and over-predicts at the low levels of income. So we saw that the better fit was having income enter the model nonlinearly, or maybe a quadratic function. How does the data look in Massachusetts? Fairly similar. So we have the linear regression, this black line. It overpredicts maybe at the low levels of income and the high levels of income, and it underpredicts somewhere in the middle. A better fit might be the cubic regression. So cubic income might fit the data better, or a linear log regression, so logged income. We have you do this on the problem set. You have to log the x variables, see which one has a better fit, or even the y variable. The next thing we want to do is look at similar sets of regressions. Okay, so remember in lecture notes 8, we looked at a series of regressions in the book. We looked at 7 different regressions with student-teacher ratio entering linearly with a set of controls, the percent English learners, the percent eligible for subsidized lunch, both of those in the model. That was our baseline model. And then we added additional control variables. We added specifications with interactions between school districts with a high percentage of English learners and student-teacher ratio interacted. Yeah, so this dummy variable for a high percentage of English learners in the classroom interacted with student-teacher ratios. We also have cubic, or we have polynomial terms of student-teacher ratio added to the models in columns 5, 6, and 7. In California, these polynomials played a large role. They're statistically significant independently. So each of the coefficients on student-teacher ratio squared and student-teacher ratio cubed are highly statistically significant. We decided that they're important variables to include in the model. We also decided that the interactions between student-teacher ratio squared, student-teacher ratio cubed, and high EL were important interactions in our model as well. So our preferred specification was column 6 back in lecture notes 8. We also looked at F-tests on those coefficients. So F-tests of the joint hypothesis that student-teacher ratio squared and student-teacher ratio cubed were both equal to 0 were rejected with 95% confidence in all specifications. So that indicates that these are important variables to include in our model, so we did. We also looked at the results of an F-test of the joint hypothesis that all the interaction terms were equal to 0, and we rejected this with 95% confidence, so we decided that those were important variables to include in our model. So again, column 6 was our preferred specification. So let's go back to the Massachusetts results and see how they compare. Okay, so here's column 1, the relationship between student-teacher ratios and test scores with no control variables in Massachusetts. We get a coefficient of negative 1.72. Now let's add in the additional control variables. Additional control variables in this case are percent English learners, the percent eligible for free lunch, the district income in logarithm, the log district income. Again, adding the additional control variables causes the main coefficient, the coefficient of interest, or the coefficient on student-teacher ratios to decline in magnitude. Again, suggesting that when we left these variables out of the model in column 1, there was omitted variable bias, and this coefficient was biased upwards in magnitude. So adding these additional control variables caused this variable to decline in magnitude, so we removed some of that omitted variable bias. So these are important variables to include in the model. So we're going to prefer column 2 over column 1 in Massachusetts, same as in California. Now we're going to look at adding district income squared and cubed relative to district income logged. So how does that affect our coefficient on student-teacher ratio, a coefficient of interest? Well, not a ton, not much. So we can still say, or we can say that we don't have a preference in terms of student-teacher ratios, the effect of student-teacher ratio and test scores between columns 2 and 3. This is our variable of interest. Adding different functional forms of income doesn't seem to really affect that coefficient. How about column 4? So now we're adding polynomial terms of student-teacher ratio, just like we had in California, except now each of the coefficients on student-teacher ratio squared, and student-teacher ratio cubed are not statistically significant. In California they were, and we rejected the joint hypothesis that they're all equal to 0, indicating that these polynomial terms are important in California. Here we fail to reject those hypotheses, so that suggests that the polynomial terms are not as important in Massachusetts. Okay, let's look at some model fit statistics to see how Model 4 compares to Model 3. So one thing we can do, so these are just individual tests of the significance of the coefficients on student-teacher ratio squared and student-teacher ratio cubed. What if we specify joint hypothesis about all three of these coefficients at once? We're going to specify that the hypothesis that all of them are equal to 0 simultaneously. We're going to test that hypothesis with an F statistic. So let's look at the results. We're in column 4 right now. The results that student-teacher ratio squared and student-teacher ratio cubed are equal to 0. Our F-stat is only 0.45 with a p-value of 0.641, so we fail to reject that null hypothesis. So that's a good indication that these variables, these additional variables, student-teacher ratio squared and cubed, are not important predictors in Massachusetts. How about column 5? So we're going to add here an interaction between the dummy for high percentages of English language learners in the classroom interacted with student-teacher ratios. So we're adding this %EL dummy and then the interaction term. We found in California that was an important predictor of test scores. It was important to have this interaction term. But remember that the average number of, or the average percentage of English language learners in California was 15.8 and only 1.1% in Massachusetts. So that might be an indication that high EL is not going to be an important predictor in Massachusetts. Indeed, we see that when we have % English learners entering the model in the previous specifications, that coefficient is not statistically significant as it was in California. So when we add the interaction term, again, it's not statistically significant. The dummy variable itself is not statistically significant, but the interaction is also not statistically significant. And we can look at F-tests on the joint hypotheses for those coefficients. All student-teacher ratio variables and their interactions are equal to 0. In this case, we do reject the null hypothesis, meaning that at least one of the coefficients is not equal to 0. It's probably the case that the coefficient that is driving that is this coefficient here, the coefficient on student-teacher ratios itself. So we can't use the F-test to rule out column 5 being an important specification. Column 6, we are simply removing %EL from the model and seeing if that has an effect on the main coefficient of interest, student-teacher ratio. So when we do that, we remove any measure of %EL in the classroom, % English learners in the classroom. The coefficient on student-teacher ratio really is not changed relative to when we have it in the model, except when we have the interaction, but the interaction we have to count for whether or not we're in high EL or low EL districts. So we should be comparing column 6 to column 2 and 3. It really doesn't change much, so that's an indication that this % English learners is not an important variable in Massachusetts. So going back to the beginning of lecture notes 10, when we said how do we determine if an omitted variable is an important variable to include in the model, well, here we've left it out of the model and compared the effects to model specifications where we include it in the model, and it really doesn't have an effect on the coefficient of interest, so we can say that this is %EL in Massachusetts is not really an important variable. So let's look a little more at the model fit statistics. We've talked about columns 4, 5, and 6. Now we're going to look at the F-test on the joint hypothesis that district income squared, and district income cubed are all equal to 0. Should we include each of these? should we include the squared and the cubic terms in the model? We reject the null hypothesis in every model where we include those at the 95% confidence level, so those are important variables to include in the model. Another thing to notice, the R squared again goes up when there's additional controls are added. When the additional controls are added, that's the same in California, so going from column 1 to column 3. It doesn't appear to make a large difference in terms of R squared, whether or not we include income cubed or logged, but the F test is large, suggesting that the cubic is a better functional fit. The most important thing, though, is we are interested in student-teacher ratios, not income for this model. So income is just a control variable. We're interested in the effect of student-teacher ratios on test scores. So going from column 2 to column 3, where we have income entering logarithmically versus quadratically, or a polynomial of income, really doesn't have that much of an effect on the student-teacher ratio variable or coefficient. So for this case, it doesn't really matter which one we choose, just as long as we're controlling for income in some form. In column 4, we tested the nonlinear relationship between student-teacher ratios and test scores for Massachusetts. In California, we saw that the cubic best fits the data. Here, the F-test on the student-teacher ratio squared and student-teacher ratio cubed terms fail to reject a null. So in this case, the linear model seems to be fine. Student-teacher ratio is entering linearly, seems to be fine, so we can just have student-teacher ratio by itself. There's no evidence that %EL has a nonlinear effect as it did in California, which could be caused by the low percentages of %EL in Massachusetts on average. So in Massachusetts, the preferred model is column 3 because the results do not seem to be sensitive to adding the %EL into the model. So we can, again, in column 6, we remove %EL altogether. It doesn't seem to affect the coefficient on student-teacher ratios, so we can just forget %EL in Massachusetts and look at student-teacher ratio by itself. So column 3 is our preferred specification in Massachusetts. So let's look at external validity. How do we compare the results? So here the book is giving you the coefficients in each state. So the linear model in California produces a coefficient of negative 0.73, or the coefficient beta hat student-teacher ratio, negative 0.3, or an additional an increase in students per classroom. One more student per classroom reduces test scores by 0.73. In Massachusetts, one more student per class reduces test scores by 0.64. But then, again, the tests are in different units, so we need to look at the standard deviations, so we need to normalize them to some extent. So here the book is showing you the estimated effect of 2 fewer students per teacher in units of the points on the test, so 1.46 in California versus 1.28 in Massachusetts, but the standard deviations are going to be 0.076 in California and 0.085 in Massachusetts. Notice that the standard errors on these coefficients are, if we add or subtract these to the coefficient estimates themselves, those confidence intervals are going to include the estimates from the other state. So that's going to be evidence in support of external validity. So we see that adding controls in both states reduces the standard or the student-teacher ratio coefficient. So it removes omitted variable bias in both states. There's high statistical significance in both states, meaning that student-teacher ratios are important predictors of test scores in both locations. The California estimates are more precise because of higher N, or higher number of observations. Remember, our standard error estimates, or standard errors, are dependent on the sample size. Comparing the change in the standard deviations is akin to normalizing the results, so we should be focused on the last column here. And the takeaway is that the results are statistically indistinguishable from one another given the standard errors, or the confidence intervals around these estimates include, the confidence interval in California includes the effect size in Massachusetts and vice versa, and therefore the California results are externally valid to Massachusetts. In other words, the effects in California, we can extrapolate those effects to being essentially the same in Massachusetts. It's not very often we have data like this, not very often that this happens. So that was external validity. Now let's think about the internal validity of the California test score analysis. So the 5 threats were omitted variable bias, functional form, errors in variables or measurement error, selection bias, and simultaneity. So we've already discussed omitted variable bias a lot in this context. We found that just regressing test scores on student-teacher ratios results in bias coefficients. So we need to control for additional variables. We needed to control for income, the percentage of English learners in the classroom. Those were important variables to control for. In California, percent EL was the most important omitted variable. In Massachusetts, income was the most important omitted variable. If these control variables are adequate, then our sample is effectively random. We don't have omitted variable bias anymore. In other words, the error term with the control variables is uncorrelated with student-teacher ratio. So the expected value of U, in other words, is there correlation between U and student-teacher ratio conditional on income, percent EL, and lunch? If there's not, if this is equal to 0, then we removed omitted variable bias and we have an unbiased estimate of the effect of student-teacher ratios on test scores. But there's no real way to know this for certain. It's just an argument. There's always going to be additional omitted variables, so we will always have biased estimates of our coefficients. It's just, how biased are they? Do we believe our results? That's the question we need to ask ourselves. For functional form, we've explored a variety of functional forms, including student-teacher ratio squared, student-teacher ratio cubed, interactions of student-teacher ratio and percent EL. We could explore more, but the results are likely to be not really affected by additional interactions. So I would argue that we've gone far enough. We've decided that at least in California, there's important nonlinearities that we need to account for, and we've explored those nonlinearities in Massachusetts. We've done our due diligence here. How about measurement error? We need to think about whether or not student-teacher ratios are recorded accurately. In other words, is the class size recorded accurately? Might it be the case that students have moved in and out of the districts since we've recorded these class sizes? If so, should we be concerned about it? If it's only one student in one school district, maybe not. But if there's a systematic exodus from California, for example, maybe we should be concerned about that. Income's not usually perfectly recorded, so there's going to be some measurement error there. We just need to think about this in our context, or whatever context you're estimating. Selection bias: the data covers all schools in California, California school districts and Massachusetts, so there's no reason to believe we have selection bias in this context. But if we had selected a sample of school districts, maybe only schools in LA or something, that might be a biased sample. Simultaneity. This would require that performance on test scores affects student-teacher ratios. So we need the causality to go not from student-teacher ratios to test scores, but the other way. This could happen if low-performing school districts receive more funding to lower class sizes by hiring more teachers. We could go to we could look this up. We could find out if the government has allocated more funding to districts with lower test scores on average. It turns out they haven't, so this is not an important concern in this context. Okay, so for lecture notes 10, we have thought about how to assess studies. So what this is good for is if you're doing your own study, if you're doing your own econometrics, you can use this as an outline for how to evaluate your own work. But also, if you're looking at studies from other people, if you're in a job where you're required to evaluate the work of other people, you look at academic papers, you can use this as a framework for evaluating other studies as well. You can think about, are the results externally valid? Do they apply to different contexts? So if maybe you are employed by a Colorado school district to find out, and they ask you, how would reducing class sizes impact test scores? You could look at studies in California and see how class size affect test scores in California, and you can think to yourself, do those results apply in Colorado? Are the results externally valid to Colorado? Maybe you don't have enough money to conduct your own study in Colorado, so you need to rely on tests or analyses performed in other states. The questions you should ask yourself is that, are the results externally valid to your context? But then also, were the results internally valid for the study that you're looking at? So if you pull a study off of Google Scholar and the study's evaluating the effect of class sizes on test scores in California, you need to ask yourself, was this study done well? Are the results internally valid to California? So you can go through each of these threats to internal validity: omitted variable bias, misspecification of the functional form, measurement error, selection bias, simultaneity. You can decide whether or not the results are internally valid. Or in other words, is it a good study to begin with? So there's a lot of studies out there that are good, a lot of studies out there that are bad, and this is a framework for evaluating them.